screen? Hello. Can you confirm if you can hear me and see my screen?
Yes, sir, we can see, sir.
Okay, great. Okay, so let's get started with the agenda for this week. So this is week 3, and what has been discussed in this week is kinematics. Okay, so if just to recapitulate what we discussed in the previous session, we described or we went through how to describe basically the mathematical representation of a robot. So in the previous session we saw mathematical representation of a robot. Right, so we saw that in there are joint variables, then we have link lengths, and then two other parameters, that is link offset and link twist or twist angle. So these four things we listed them under the name DH parameters, right? And what we'll see today is how to basically exploit these DH parameters to basically express the kinematics of our robot. So if I just quickly uh, draw a flow chart of what we have seen till now and what I will cover or has been covered in the lectures, so it would be something like this. So you have a so I'm just drawing a representative diagram. So this is the robot, any robot, just it's a representation, right? Then from here what we did, we did DH parameters, basically Li, Di, alpha I, theta I, right? All these things we calculated. Okay, so this is our what we can say as mathematical model. And this has degree of freedom as well. Okay, now after this what we have is we have some equations right, that relate these two quantities, right? We This is what we will discuss today, right? So this is kinematics, right, where x is the task space variable and this capital theta is the joint space variable. Okay, so this is where we are at the current stage, and today our focus would be this block. Right, so this is the focus of today's session. Alright, so I presume you have the familiarity and you have practiced how to basically write DH parameters and how to construct homogeneous transformation matrices, because we will be now using those concepts to derive the kinematical relations between the task space variable and the joint space variable. Okay, so let's get started with it. So before we start, it is again important to reiterate that we need to first identify the degrees of freedom of the system. Why this is important is because this governs what kind of relations we can uh, basically find out between the two sets of variables that we have, right? So for a 3D manipulator, that is, it can move in the three-dimensional space and not restricted to just a plane. For the 3D manipulator, if the number of degrees of freedom, that is n, is less than 6, then it cannot achieve all positions and orientations of the end effector, right? If n is equal to 6, then it can achieve all position and orientation, right? And if n is greater than 6, then we call it as a, then also it's possible and it's called as a redundant system. Redundant system means that we will revisit this term later also in this session. So redundant systems are systems in which it can reach any position and orientation and more than one configuration is possible. More than one configuration possible. Okay. So now the next is the spaces, the two spaces which I talked about, right? So first is the task space, also known as the end effector space. End effector space, right? So this is the space of the position and orientation of the end effector. Right, so in a general case, this x would include basically the x coordinate of the end effector, the y coordinate of the end effector, the z coordinate, and similarly the orientation, let's say phi, theta, psi. Right. So this is a 6 cross 1 vector. This is the These are the variables of the task space, right? And on the other hand, we have the joint space. The joint space are variables related to the degrees of freedom and their values basically, right? So degrees of freedom are the joints. So what values each of those joint variables are taking, that that basically makes up the joint space, right? So for, let's say, for a 3R manipulator, right? For a 3R manipulator, the joint space will be theta 1, theta 2, and theta 3, right? And the size of the joint space is 3 cross 1, so the size of the joint space is n cross 1, where n is the number of degrees of freedom. Okay, all right. So these are the two spaces, and what we had seen last week is that we have the task space variables, we have the joint space variables, and we are going back and forth between them, right? So going this way is forward kinematics, or as described in lectures as the direct kinematics, and going from task space to the joint angles is the inverse kinematics, right? So in control algorithms, basically we make use of both these expressions and relation, but in generally fk problem is simple and straightforward. It's just matrix multiplication, simple and straightforward matrix multiplication, and inverse kinematics is trickier, right? Bit harder and requires requires finding solution for multiple transcendental equations. Right. So Fk and Ik. Right. These are the two types of calculations that you would do when you would be dealing with the kinematics of a serial of any robot, right? Okay. Any questions still here? Okay, let's go ahead. So, what I will describe today is first the forward kinematics, then the inverse kinematics, and then we will see the concepts of workspace and how to find workspace, right? So, I will use a very simple example of a 2R manipulator, and I will derive the entire forward kinematics and inverse kinematics for the 2R manipulator. And I would suggest you should also like follow along with me and do those calculations as I proceed. Okay. So let me draw the setting in which we will work for this session. This is frame 0. Then let me first draw the links. This is the end effector, right? And then we have the frames. So Nina, this is more of a doubt solving and rediscussion of what has been covered in the lecture slides, lectures. So this does not cover anything outside the lectures. It's more or less around the lectures, but I try to go into specific of certain concepts which might need a more detailed looking into, and I also solve some questions and around those concepts. So you can use this session for clarifying your doubts about the content that you see in the lectures. Let me just draw this. I think this should be enough. Okay, and finally we have the end effector. Let me draw this using this. Ideally it should be Okay, so this should serve us well. uh, yeah. Okay, so let me just name these frames. So this is frame 1, this is frame 2, and this is the tool frame as it is referred in the lectures. So this is the end effector frame, right? This is of length L2, this is of length L1, right? This is theta 1 positive in the anti-clockwise direction, and I should place this somewhere else. Oh, this is theta 1, this is theta 2, and yeah, this is frame 2. Okay, so frame 0 is the base frame, frame 1 is attached to the first link, frame 2 is attached to the second link, or is at the second joint attached to the second link, moves with the second link, and frame tool frame is at the end effector and it is also attached to the second link and moves with the second link. So basically we have the, so the first thing is to clearly mark the frames. So this is the inertial or the base frame, inertial or the base or the world frame, right? Then there is one, it is attached to link 1, then there is 2 attached to link 2, and then there is the tool frame attached to the end effector. Okay, so once we have these frame conventions in our mind, the first step basically is to write the DH parameters, which is very straightforward in this case, and to write the transformation matrices, right? So what I will do, I will directly write the transformation matrices. So if you remember, transformation matrix from this nth frame to n minus 1 frame, this matrix is written as R n to n minus 1, and then position in the n minus 1th frame, and then this is 0 0 0 and 1, right? This is a 3 cross 1 vector, this is a 3 cross 3 matrix, right? So here how many such matrices we will have? We'll have to write first from tool to 2, then we'll have to write 2 to 1, then 1 to 0, right? And finally what we want to calculate is the transformation from tool to 0, right? So that is calculated as, so we have this then multiply with this, and then multiply it with this. Right, so this is sequence of transformations. Okay, so what we'll do now, we will write each of these three matrices, and yeah, and then we will multiply them, right? So let's do that. So the first transformation matrix we'll write is from 1 to 0. Right, so the first, now a bit more on the notations. So as we discussed in the last session, C1 is cos theta 1, S1 is sin theta 1, right? C12 is cos theta 1 plus theta 2. Okay, and similarly for S12, it is sin theta 1 plus theta 2. Okay, so for the first, it will be C1 minus S1, S1, C1. This is the rotation part that I am writing. So this is a 3 cross 3 rotation matrix part. And this is 0, 0, 0, 1, and the position is 0 because frame 0 and frame 1 are coincident, right? So if you see here, frame 0 and frame 1, they share the same origin. So there is no translation, there is just a rotation, and the rotation is about the z axis, right, which is coming out of the plane. So a rotation of theta 1 about the positive z axis. So the rotation matrix is cos theta 1 minus sin theta 1, sin theta 1, cos theta 1. And this is 1 because this is corresponding to the z direction, right? So this is the first transformation matrix. Okay, now let's write the next one. You can first try writing this on yourself, and before basically I write it. Just take 1 minute to think and write this transformation matrix. Then I will write it, and we can match our matrices. Okay, so the second one, if you see the our frames, so we have to find relation between the second frame and the first frame, which is the maroon one and the green one. So the green frame is rotated about the z axis about theta 2, and there is a translation of L1 along the x axis of the frame 1, right? So the origin of frame 2 is translated along the x axis of frame 1 by a distance L1, and the frame 2 itself has been rotated by angle theta 2 about the z axis of the frame 1, right? So using this information, we can write this. First the rotation part, right? Any doubts in this? Anyone? And finally, last one is very straightforward too, right? But sometimes, you know, simple things become less obvious. So now just again take a minute to think what should be the transformation between the tool frame and frame 2. So if you notice, as I mentioned, frame 2 and frame the tool frame both are fixed to the second link, so they both move together. So there is no difference in the orientation of these two frames. So basically, the rotation part will be an identity matrix because the orientation is exactly the same. The only difference is in the translation. So the tool frame is translated by a distance L2 along the x-axis of the second frame, right? So I repeat once again, the orientation of the tool frame and frame 2 are exactly the same. So the rotation part of the transformation matrix will be an identity matrix. However, the tool frame is translated by a distance L2 along the x-axis of the second frame. So the translation part will have L2 in the x direction, right? So this is L2, and since it's an identity matrix, so it will be okay. So now we have all these three matrices, right? So what we do next is start multiplying, right? So we can start multiplication in any order. So let's first multiply the last two matrices, right? So that will give us tool to 1. That will give us tool to 1, right? So this is 1, this is 1 to 2 t, and then 2 to tool t, right? I'll directly now write the multiplied matrix. Okay, so let's see. Basically, we have to multiply this matrix with this matrix. Okay, so taking the first row of the second matrix and then multiplying. So again, this matrix multiplication I will do here only. Just bear with me while I multiply these matrices. So this will be C2, this will be C2, then 0 0 0, then we will have minus S2, then rest 0, then we will have all zeros, and then we will have L2 C2. L2 C2 plus L1. Please keep multiplying on your own. And here it will be L2 S2. 0 0 0. And then there will be 0, then there also 0, then 1, and then 0, and then this will be 0 0 0, and this will be 1, right? So this is 1, and then finally we have to multiply to get the desired transformation, that is from tool to 0, that is 0 to 1, and then 1 to tool. So this will be and this is 0 0 0 0 0 0 1, right? And this is C2 minus S2 0 S2 C2 0 0 0 1 0 0 0 2 C2 plus L1 2 S1. Right, so now again I request you to multiply this on your own so that if I do any mistakes you can point it out right here. So now we have multiplied this, and we will use some trigonometric identities to simplify these expressions. So this c1 c2 minus s1 s2, that is cos theta 1 cos theta 2 minus sin theta 1 sin theta 2. So this is c12 cos of theta 1 plus theta 2, and similarly c2 s1 plus s2 c1, that is sin 1 2, right? So this is c12 minus s12 s12 c12, and 0 0. Okay, and here what we have is L2 C2 C1 plus L1 C1 minus L2 just a second, L2 C2 C2 C1 I think here it would be, yeah, here it's S2, right? Here it is S2, yeah. So here it will be S1 S2. Okay, so here it becomes minus L2 S1 S2, right? And this becomes L2 C2 S1 plus L1 S1 plus L2 S1 C1, right? And then 0 and then 1, right? Now again you can see that L2 is multiplied with this and this, and if we club them together, then it is cos theta 1 plus theta 2, and similarly for L2 we have S2 S1, and this would be, yeah, this would be S2 C1, and this is sin theta 1 plus theta 2, right? So the final matrix, the final homogeneous transformation matrix from 2 to 0 that we have is C12 S12 0 0, then S12 C12 0 0 0 0 1, zero zero 1 0, and this is L1 C1 plus L2 C12, and this is L1 S1 plus L2 S12, and this is 0, this is 1, right? Now what we wanted to basically find out is what is the position of the end effector in terms of the joint variables, right? Position and orientation, right? So from the transformation matrix, we find out the position and orientation of the end effector in the base frame. Okay, and that is, so The position part is given by the last column of the, as you know, this is the position part, right? So that is given as L1 C1 plus L2 C12, and the y coordinate is L1 S1 plus L2 S12, and the z coordinate is 0. Right, and the orientation, just give me a second. Right, and the orientation is the rotation matrix, which corresponds to a rotation of theta of theta 1 plus theta 2 for the z axis. So the orientation is theta 1 plus theta 2. Right, so from the forward kinematics we have both the orientation and the position of the end effector, right? Any doubt in this derivation? Okay, so what we discussed just now is the forward kinematics or the direct kinematics of a 2R manipulator, and the same process can be repeated for any robot once we basically write the DH parameters, and then the steps remain the same. You write the DH parameters, you write the transformation matrices, and then after that you multiply them in sequence and you get the uh, forward kinematics of your point of interest in the base frame, or in fact you can write it in any other frame as well. Now moving ahead, the next is the inverse kinematics. Right, so inverse kinematics. So inverse kinematics involves that the task space variables are known and we have to find out this. Okay, so now this involves basically what we have in the forward kinematics case of a 2R manipulator, that is the end effector x is L1 C1 plus L2 C12 and the y is L1 S1 plus L2 S12. So basically we have to solve this system of equation to get theta 1 and theta 2. And this becomes increasingly hard with increasing degrees of freedom of the system. So there would be like and in order to basically calculate the have a unique solution of inverse kinematics, we should have number of equations equal to number of the joint variables. If we have more number of equations, then the inverse kinematics solution is not unique. Basically, there are infinite number of solutions, and if for certain cases we get no solution, then inverse kinematics no solution of the inverse kinematics problem implies that the point and the position and the orientation of the end effector that we are trying to calculate the joint variables for, that is not in the workspace of the robot, right? So inverse kinematics is related to what we will see next, the concept of workspace, right? So workspace is basically what is the area or the volume when talking about 3D that we can reach using our robot, right? So again we will use the 2R manipulator example to see the inverse kinematics problem. Hello, if you have any doubts, you can please ask or write in the chat. Okay, so 2R manipulator example. And one thing to note is that inverse kinematics is like not the same process for all the robots you will encounter. It's basically kind of a unique process depending on the robot, right? So for certain configuration and arrangement of joints, you can have a certain way of doing inverse kinematics, but for different robots it might not be applicable, which is different from direct kinematics, where there is a standard way to do direct kinematics for all the robots that are there. Like you basically compute the h parameters that you can do for any given robot, and then you write the homogeneous transformation matrices that also you can do for any given robot, and you basically then just multiply them to get those final transformation matrix, and you extract the position and orientation from that matrix, right? But that's not the case for the inverse kinematics problem, right? So what we will see here is like for the 2R manipulator, and that can be extended to like other serial manipulators, right? But it's not like a standard thing which is applicable for all types of manipulators that you will encounter, right? So as I wrote above, we have to find solution of theta 1 and theta 2 such that we satisfy these equations, right? Xp and Yp are now known, right? So Xp, Yp are known. Okay, so let X be defined as Xp and Y be defined as Yp. Then first what we do is we do x square plus y square, right? This is the first step. So this is L1 C1 plus L2 C12 square plus L1 S1 plus L2 S12 square. And then if we open this, right? Now we know that sine squared theta plus cos squared theta is 1. So this will become L1 square plus L2 square, and these terms will become 2L1 L2 C2, right? Because this plus this is the you can use the formula of cos theta 1 minus theta 2, right? And here theta 2 is theta 1 plus like cos alpha minus beta, right? Where alpha is theta 1 plus theta 2 and beta is theta 1. So what remains is theta 2, right? So just by doing this manipulation, we have this relation, right, in which the only unknown is cos theta 2, right? So we have the relation for theta 2, it is plus minus cos inverse, and here it will be x square plus y square minus L1 square minus L2 square by 2 L1 L2. Any doubts in this?
No.
Can you repeat? Okay. Why the significance of this I will discuss in a while. So we have theta 2. Now we have to find out theta 1, and theta 1 is basically given by this relation, which is a tan 2 yx where k2 is L2 S2 and k1 is L1 plus L2 C2. Right, so this gives theta 1. So once we know theta 2, we can calculate the value of theta 1, right? And this plus minus basically corresponds to two configurations, that is commonly known as, in case of 2R manipulator, as elbow up and elbow down. So basically what this means is that if I have to make my manipulator reach this point, then I can go like this or I can go like this, right? So this gives different values for theta 1 and theta 2. This is right. So we have two solutions. This is elbow down and this is elbow up, right? So depending on the you know the branch of solution, as it's called, the branch of solution that we choose for theta 2, we will get different value for theta 1, right? So this is a very a quick demonstration. It's a very simple system, a 2R manipulator. For 3R manipulator we have some more complexity, and for higher degrees of freedom it is so we use computers to solve those equations, right? Any questions on the inverse kinematics of the 2R manipulator, on the concept of inverse kinematics? Okay, so now we will discuss about the concept of workspace, right? So, and that is closely related to the concept of workspace is closely related to the points or the orientations where we have valid solutions to the inverse kinematic problem, right? So for a 2R manipulator, right, valid inverse kinematic solutions, we get we are able to solve the inverse kinematics equations, then it's in the workspace, right? So for a 2R manipulator, for a 2R manipulator, wait, let me use the next page. Something happens here. For a 2R manipulator, we have theta 2 equal to cos inverse x square plus y square minus L1 square minus L2 square by 2 L1 L2, right? Now we know the relation that cos theta should lie between this range, right? If cos theta is not in this range, which that means it's not, there exists no solution for theta 2 which basically satisfies this. So if we use this relation, right, so using this mathematical relation or constraint, as you can say, on the values, so to keep cos theta between -1 and 1, uh, we have certain constraints on theta 2, what values that it can take basically, right? So what we can write is -1 to 1, and we have this expression for cos theta 2, that is x square plus y square minus L1 square minus L2 square, right? So this should lie between -1 and 1, and that is equivalent to uh, this is equivalent to saying, right, that basically what how we can rewrite this is, let's say we take -2 L1 L2, we basically write these two inequalities separately for once, okay? And this is, and this is 2, right? Now if we further rewrite this, this is L1 square plus L2 square minus 2 L1 L2, right? And that should be less than x square plus y square. And same way here we can write x square plus y square should be less than L1 square plus L2 square plus 2 L1 L2. And so this implies that what we have is L1 minus L2 square is the lower bound of x square plus y square, and the upper bound is L1 plus L2 square, right? And basically for if this is the origin and this is x comma y, right, then the x square plus y square gives the distance between these 2 points. This is x2 square plus y2 square, right? And L1 plus L2 square is basically the radius of a circle, right? So right, and the other is this circle, right? So this is radius is equal to L1 plus L2, and this is radius is equal to mod of L1 minus L2. Why am I using mod? Because L1 can be greater than L2 or smaller than L2, so we will take the difference, right? And that is the radius of the inner circle, right? And basically what we have is this area which I am shading. This is the reachable area. So this is the workspace of a 2R manipulator. Any questions regarding this?
No, sir.
Okay. So what we find out is that the workspace is this shape we can call as a ring or an annulus, right? It's an annulus or a ring, right? And now where workspace is useful is basically when we are designing manipulators or these serial robots for certain applications, and we want to know while designing that whether my workspace is sufficient to do my desired task or application, right? So and workspace maximization is something which is commonly done, right? So I'll quickly show example for this 2R manipulator itself, that what what scenario is workspace being maximized. So workspace maximization, right? So since we are talking about 2D, in 2D that is equal to maximize the area of the workspace, maximize the area. In 3D it would be maximizing the volume. So the area of the workspace W here is given by the area of the bigger circle minus area of the smaller circle, right? So the area of the bigger circle is pi r square. R is L1 plus L2, right, minus area of the smaller circle, that is L1 minus L2, right? And when we simplify this comes out to be 4 pi L1 L2, right? Now the constraint that we have is that L1 plus L2 is a constant, let's say C, right? So which implies that L1 can be written as C minus L2. So which implies that area can be written as 4 pi L1, or let's say L2, and C minus L2, right? So this is 4 pi CL2 minus L2 square, right? Now we have to maximize this area. So we know that for maximization we have dA by dL2 equal to 0, which implies that uh, C minus 2L2 equal to 0, which implies that L2 equal to C by 2, and that implies that L1 equal to C by 2. And the conclusion is that area is maximum when L1 is equal to L2, and that makes intuitive sense as well, because in that case this unreachable circle goes down to 0 when L1 is equal to L2, right? So this is the maximum workspace condition. Okay, any questions here?
No, sir.
Okay. Okay, now the analysis of a 3R manipulator workspace is, so the analysis of a 3R planar arms workspace is interesting, is more interesting, and there are like more layers to it. Okay, so basically I'll use the lecture slides for this. So yeah, so this is the 3R manipulators workspace. So here we can see that there are 4 combinations. Like in 2R case there were like only 2 circles. Here there are 4 circles. So the outermost one is the maximum reach, that is L1 plus L2 plus L3. Then the second is L1 plus L2 minus L3. The third one is the L1 minus L2 plus L3, and the smallest one is L1 minus L2 minus L3, right? So now each of these reasons have like the behavior of the arm is different, right? So first we have to see is that in 2D, as we have discussed last week, that we have 3 degrees of freedom. We have x, y, and the orientation, right? X, y, phi of the end effector, right? And basically, so 3R is sufficient to achieve any position and orientation in its workspace. Okay. Now what we have here is that we have 4 circles of different radii, right? So first is what we call as the reachable workspace. So reachable workspace are all the points that lie between the maximum reach and the minimum reach, right? So the maximum reach is outer one and the minimum reach in the inner one. All points between those are reachable, that is there is at least one configuration of the arm, that there exists at least one configuration of the arm in which the end effector can reach that point xy, right? So that is reachable workspace. Okay, now the other division is the dexterous workspace. So all points between the radii, the inner two ones, right? So this L1 minus L2 plus L3 and L1 plus L2 plus L3. So this middle zone in which this schematic has been shown. So basically what is possible in dexterous workspace is that we can achieve the same position and orientation of the end effector in two different or more than one configuration, right? So as you can see, for the same position and orientation of the end effector, this is one possible configuration and this is another possible configuration. And the points where such thing is possible lie in this region, and this is called the dexterous part of the workspace, right? So all points inside dexterous workspace can be reached with any phi, right? Phi is the uh, phi is the basically the sum of all three angles, right? So that is, so there are like many different ways in which the same point can be reached in the dexterous workspace, right? And we see that as the size of the end effector L3, size of the end effector, that is L3, increases, the reachable workspace increases and dexterous workspace decreases, right? Because as L3 will increase, uh, basically this you see L1 plus L2 minus L3. So as L3 will increase, this radius will get smaller and smaller, right? So dexterous workspace would go down, but since L3 is being added here, so the reachable workspace will keep on increasing, right? So that is a very, you know, interesting observation. And the example that is cited here is that with a long stick we can reach far, right? You can imagine with a long stick, but we have less freedom in orientation, because that long stick cannot be oriented with that freedom as a smaller stick. So any doubts in the basically definition of reachable and dexterous workspace? I will write these, will draw this here as well. So what we have is, we have L1, L2, L3 and this. So we have four circles. I hope I draw round circles. Right. Okay. This R1, this R2, this R3, and this is R4. And I can mark this as, this is A0, this is A1, A2, A3 and A4, right? So A0 and A4, these are unreachable. Then all of A1, A2, A3, these are reachable, and all of A2 is dexterous, right? And R1 is L1 minus L2 minus L3. R2 is L1 minus L2 plus L3. R3 is L1 plus L2 minus L3, and R4 is L1 plus L2 plus L3, right? And the definition of reachable is that at least one configuration in which that end effector pose can be achieved. And dexterous means that there are more than one possible configurations to achieve the same end effector pose, right? So that is one crucial thing to keep in mind about the dexterous and the reachable workspace. And where this dexterous workspace becomes useful is when we want to avoid obstacles or collisions in the working environment of the robot. So let's say has if the point where the robot has to reach is in the dexterous workspace, and let's say in one of the configurations it is colliding to a certain with a certain obstacle, then it has a different configuration in which it can still go that point. But let's say if the point of interest is in the reachable workspace, and the configuration in which the robot can reach that pose is blocked by some obstacle, then there is no other way in which we can basically reach that point. So the importance of reachable and dexterous workspace becomes more uh, crucial when we have some other constraints in the operation of the arm basically. Any questions or queries at this point?
No, sir.
Okay. So this basically sums up what I had planned for this week. Uh, the lectures have few more examples of higher degree of freedom arms, which like Puma robot and all, which we can basically go through, derive those expressions on your own, and understand better. Uh, and finally, we have the Skara robot, right? And one interesting thing is that when the degrees of freedom for 3D motion is greater than 6, right, or greater than 3 for planar motion, then we have more unknowns than the number of equations which I had mentioned. And these are what we call as redundant manipulators, right? So redundant manipulators again give us the advantage that there are multiple configurations or infinite configurations in which we can achieve a certain pose of the end effector, and that gives us a lot of freedom, especially working in obstacle filled environment. So that is the redundancy, and redundancy can also be used to exploit some other things like minimization of joint rotations, velocities, accelerations, avoiding obstacles and singularities, and minimization of actuator torques. So that redundant degree of freedom can be used, or to basically constrain the solution to a specific solution, we can basically put these kind of additional requirements, additional equation to get a unique value of theta i's, right? So so the just the inverse kinematics relations are not sufficient, because the number of equations is less than the number of unknowns, so we have to add additional equations. And if we are adding additional equations, then we add it in a way such that that is useful to us in some way, because like if we minimize actuator torques, then we are basically minimizing the energy consumption of the robot, and that is something we would like our arm to be energy efficient or move in a way such that it consumes less energy. Similarly, avoiding obstacles keeps the robot also free from damage and all, right? So those type of objectives can be achieved when there is a redundant degree of freedom in the arm, right? And the explanation of those is given in the lecture slides that you can refer to, right? So in case there are no more questions, we can end this here for this week. And what we will discuss in next week is about parallel robots and their kinematics, right? So thank you for joining, everyone, and I will see you in the next week's discussion hour. You can solve the assignments, and maybe if you have any questions, you can from the previous assignments, you can ask me right now.
Uh, Hi, Amitanshu.
Yeah. Hello.
Can you hear me?
Yeah, I can hear you.
Hi. Yes, so I have a doubt with respect to week two lectures.
Mm-hmm.
What can we, would it be possible to address that?
Yeah. Go on.
It's a, um, so it's on the parallel manipulator.
Mm-hmm.
Um, can I share my screen, or how should I go to that specific example?
Yeah. You can share your
It's
screen. I will just stop
it's
sharing.
with respect to the 3DOF parallel manipulator.
Mm-hmm.
Let me
Mm-hmm.
show.
Are you referring to the lecture slides?
Yes.
Okay, so let me just pull up the lecture slides, and maybe you can point me to the page number which I should go to. So this is,
Okay.
yeah.
Yeah.
So this is the week 2 lecture slides. Can you point me to the page number?
It's it's page number 20.
Can you repeat? I could not hear that. Hello.
Yeah, it's 204.
It's what? Hello. 204. Okay, you can present, Ninad.
Hello. Am I audible?
Yeah, you are audible. Your voice is breaking down from time to time. Uh, yeah, you can present, and I will see uh, how we can
Oh.
address that.
Okay. All right. Okay.
Right now, I'm not able to see your screen.
Let me. Are you able to now?
Uh, no, I think it's still kind of loading. Can you try once again?
Yeah. Um. How about now?
Yeah.
Hello.
Yeah. Yeah, I can see your screen.
Okay. Yes. Perfect. So, great. Um, I had a doubt with respect to the DH parameters of this 3D or parallel manipulator.
Mm-hmm.
Um, so my question was with respect to the how were the angles, how was the angle theta 1 derived, and why is alpha I minus 1 minus pi by 2? I wasn't able to exactly map these
Hmm.
two variables.
Hmm. So, one is minus pi by 2, another is phi 1, right? These two. Hello.
Hello.
Yeah, I'm just repeating your query. So, your doubt is regarding the first joint angle, that is phi 1, that is being written in the DH table, and the twist of the second link, that is minus pi by 2, right? Okay, okay. You can stop sharing now.
Yes.
I have that in the lecture slides as well, so I will continue to refer that. Okay, thank you. Just give me a moment to, just look through this mechanism. Mm, okay. Let me just again share my screen. Mhm. Okay, Ninad, can you hear me and see my screen? Hello.
Yes, I can see it. I can't hear you.
Okay, okay, fine. So let's work it through right now itself. So it says DH parameter of the first leg with respect to L1. Right. So okay. Hmm. Okay. Okay. So L1 is this link. Okay, this is a prismatic link, that is L1. All right, that comes in the joint variable of the second row. Okay, that is fine. That's the easy part. Now the theta I. First thing is theta 1. Right. So theta 1 is basically, I think we'll have to imagine this as 90 degree minus theta 1. So that is phi I. Right. So axis of R1 is this, and this is the base platform. So phi, the angle theta 1 is shown in the figure is same as pi by 2 minus phi 1. Okay, I think theta 1 is shown here, right? And so theta 1
Mhm.
is angle between the, if you from the DH convention, it's the angle between the x axis of the two consecutive frames about the z axis of the joint that we are talking about. So the base x is here, and the other x is along this. I think I will need to draw something. Let me just, what I'll do is I'll snip this from here. Okay, and let me just put it in there. Okay, I'll just add it. Let me just add it here. Okay, so that will help me draw some things on this. Yeah, so okay, okay. Hmm. So this is the x
Hmm.
one, is this is the x of the base, so this is x0, right? And
Hmm.
this comes like this, and what we have here is uh, the x would be along the joint if we take like this, right? The x1 axis. Okay, so it's like
Okay.
uh, this we take as x0, and it's like this, and here we take it as x1. Okay, and yeah,
Okay.
so and about the z, this is the z of the joint. Okay, so this would become, now here, there it is marked as pi by 2 minus theta 1. So if this is taken as theta 1, right, now the angle should be basically from this vector to this vector, so the angle should be this, right? And then, but this would be pi minus theta 1, not pi by 2 minus theta 1.
Yeah. Yes.
Was this the source of your doubt?
Yes. Yes. So my question was, so x1 is perpendicular to z1 of the revolute joint,
Mm-hmm, yeah, correct.
and then and so how did you I think this one is pretty basic for me, that so how did you decide on x1 and like which one would be y1 then?
So y1
Because
would
you took
be
x1 along the axis of the prismatic joint,
prismatic
right?
joint. So yeah, so x1 I took along the uh, so this is the first link. Okay, and yeah, x1, but wait, I think this would be then, hmm, x1 I'm taking like along the this link, this prismatic link, right? And
Okay.
this would be, but I think this would be then not x1 but x2, because this is second link. You are right, this would be x2 because this is second link. This is z1, and this for the first link. Hmm, slightly difficult to imagine there. Uh, that is, you correctly pointed out, right? That should not be x1 because this is the second joint, the prismatic one, and if we take, and that also we should not take x along it. Hmm.
should be. And then is the second axis with respect to the slides, is it taken like has the professor taken x2 and the entire number two convention for the second revolute joint, or
So what I get is that here we are writing, basically here we are writing, making three different tables, one for each leg, right? So
okay?
and each leg has a revolute, then prismatic, then spherical, right?
Yes,
So
yes,
we have 3 degrees of freedom in each leg, right? And it is revolute, prismatic, and spherical. Okay.
hmm,
So the first the first link is basically uh, this this base, like along this base platform itself. Like if you imagine, it's like this is the base platform, and we have a hinge here, right? We
yes,
have a hinge here, this link. Okay. So if this is z1, right?
yes,
And what it's mentioning theta 1, if I like, I think we should draw our own diagrams now, because it's kind of difficult to imagine this. So let's say if this is the, and this is the hinge here, the revolute joint, right? And then the link attached to it is like this. Okay.
okay,
And so this is the base, and this can rotate, right? This is what they are describing as theta 1. Okay.
yes,
Right? And then this has a prismatic joint, right? This is d, right? This is d. This can extend or retract, and finally there is the spherical one. So this is the scenario. So we have the hinge on the corner of the base platform and a link attached to it. So let's first focus just on that here is the hinge, here is the hinge, and here is the base, right? Here is the base. Now what they have marked as theta 1 in here is basically they have taken, now in this diagram they've taken this as the x, right? Now
hmm,
and this is the z1. Okay. And the angle that the lecture slides have is basically rps. And so let's just try to like kind of reverse engineer from here. So it's taking alphas a and d all as zeros, right? So
yeah,
alpha is 0, so basically the z is uh, along the z, the twist between x and the x of the x0 and x1 is basically there is no difference. So x, the other x is also in here only. uh,
yes,
no. Let me just correct myself. uh, Alpha is basically the twist between the angle between the consecutive z axis, right? About the x, consecutive z axis about the x, sorry for the confusion. So if,
mhm,
and that's why this, okay, I'm getting it now. So this z1, and we have this we have this, right? Z 0 here.
Mm.
I think the angle between these, the Z, the Z up here, right? The Z up here and the Z that is
Mm-hmm.
here, right?
Mm.
The angle between these two
Yes.
should be uh, minus pi by 2. Okay, and because that's the, because if we take this, because this axis is along here and this is up, so if I take, not rotate this like this, that's first. Wait, now the pi by 2 minus theta 1 thing, if this is the angle between this is theta 1 and okay, this is, and this would be pi by 2 minus theta 1, and joint angle is basically along Z, about Z, right, about Z between xi minus 1 and xi. Hmm, about Z.
Isn't it about x between z and zi minus one and zi?
I'm not, I'm doing about the theta.
Oh, okay, okay,
Yeah,
okay. Sorry.
yeah, that's fine. So what, I'm just like trying to reconstruct the frames how they would have taken, right? So if theta, like theta 1 they have marked as, or I should write theta I is marked as pi by 2 minus theta 1, right? And theta 1 is, so theta 1 is for sure the angle between the base and the, and this prismatic link basically, right, what we have drawn here,
Mm.
right? So this is the
Right.
prismatic thing, and so from the base, right? But rather than taking theta 1, it it's mentioned pi by 2 minus theta 1, so that means they're taking some other reference. So uh, yeah, so then it would be like the first x is here, right, and the other x would be uh, what I think, okay, if I take this angle, oh okay, then this rotation would be pi by 2 minus theta 1. Okay, so this is x and this is my first x basically. Okay. Hmm. Hmm. Let me just again draw this, so, and
Mm.
and just see if the explanation holds consistently. So this is the base. Okay, and this is the link, and this is the prismatic one. Now let me draw the frames. Okay, so we have the we have the x x marked in the image, right? And if I take and this x is like this, right? Okay, now this angle and about this revolutions axis, right? This is pi by 2 minus theta 1 because this
Oh,
is theta 1.
so
Okay.
you seem to be switching axis right now because
Mm-hmm.
uh,
Go on.
uh how is that? So you said between x1 and x0
Mm-hmm.
for that link is pi by 2 minus theta 1.
Mm-hmm.
That would be along a different plane. So I'm just trying to understand how you reach that conclusion.
No, like this plane, so this link, right? If we extend this here, this is one axis,
Okay.
and let's say this we extend here, this is one axis. So if this is the plane that we have, right? This is the
Okay.
plane that we have, and z is coming out of this plane. Okay,
Okay.
right? And uh, and we have defined this angle to be theta 1. Okay, this angle to be theta 1. So wait, did I? No, I think I marked the wrong angle here because this is theta 1, then this would be, if I extend it like this and then it would be the opposite angle of theta 1 itself. So this would be theta 1 itself.
Yeah, that should be
Yeah,
theta 1 itself.
right, this would be theta 1 itself. And if I draw this perpendicular here, right, and vertically below here like this, okay, then this would be pi by 2 minus theta 1, and down below this would be pi by 2 minus theta 1. Now
Okay.
now what would have led, which choice would have led to this is along the z axis I am rotating. Hmm, seems very weird because this is the base axis is here, and okay. Uh-huh. Hmm. Like for me, it's still coming out to be theta 1 only. I'm not able to see why
Uh,
it's pi by 2 minus theta 1. Or
so the angle theta 1 is phi 1 as per the slide. And
no,
then
theta. Uh, yeah, I mean, theta
alpha.
1 is something that is marked in the image, right?
Yeah. Theta 1 is not the name.
Theta 1 is marked in the image. So phi 1 is pi by 2 minus theta 1,
Yes.
right? So theta 1 is equal to pi by 2 minus phi 1. So phi 1 is pi by 2 minus theta 1. So this basically is what is meant here is pi by 2 minus theta 1.
Okay, so that is pi by 2 minus theta 1. It's directly given.
Yeah, so but that I am not able to decode right now is what assignment of frames
Okay.
would have led to pi by 2 minus theta 1 being the, you know, being the joint angle and not just theta 1, because
Hmm.
that seems to be a more plausible selection of frames.
So for sanity check,
Uh-huh.
uh, alpha I minus 1 is rotation or yeah, like degree, how many degrees the axis, sorry, degrees between z axis
Z
and
axis.
vertex.
Yeah.
Okay.
Mm-hmm.
and theta one is between x-axis
X-axis,
above
yes,
z1.
yes, yes, yes.
Okay, okay, okay,
So if you see like
okay.
the minus pi by 2, right? Minus pi by 2 is basically the rotation of the z axis, right? From the first to the second. And if you
Okay, yeah.
if you take that, then basically,
Okay, yeah.
so then the z would be about x minus pi by 2. Minus pi by 2. I think second one I am getting one assignment of frame. Second one I am getting is that uh, if I rotate, so can you see
Hmm.
my highlighted mark?
Yes,
If I
yes, I can.
rotate, if I rotate about this by minus pi by 2, then I come from
Hmm.
here to this z axis,
Oh,
right?
right, right. Yeah,
Right.
yeah, yeah. You have to rotate clockwise to get there when
Yeah,
we use
clockwise
the
to
right
get there.
angle.
Yeah,
Yes, yes. That I realized. Yeah.
yeah.
Okay.
Now it's
Second
just
one is
that
still.
the first one, that pi by 2 minus theta one thing, if again, maybe I think like I'll also need some more time to exactly draw those axes, and maybe uh,
Yeah,
I can discuss this once again, maybe next weeks for with some proper sketches.
yeah,
Okay,
yeah.
and
I'll try it out as
yeah,
well,
and you can
and
also
if I
work through and uh,
yeah, if I come up with something, I'll
yeah,
let you
yeah,
know. Oh,
okay, yeah. But thanks for raising
thank you,
this.
Amitabh.
Good. It's a good thing to just think about.
Yeah, thank you for discussing it with me. Thank you.
Okay. Uh, yeah. So I think I will end for now, and I will see you guys in the next week's discussion hour. Okay. Uh, Goodbye.
Thank you. Bye bye.